last week before our break. A couple of things. I've had to shorten the PowerPoints into smaller modules. And also, I'm still struggling a little bit with the technology. So the use of the pen I'm trying to use is going to be a little iffy. So bear with me. I'm going to go through this first section kind of quick because we already did it. So, and then I'll slow down for later sections. Okay, so remember that our strong acids are 100% dissociated. So you have the strong acid here, and then after it hits the water, it's going to react with the water to form 100% of the ions. So here is the H3O plus and A minus. Notice it's the same amount as the original acid because the mole ratio is 1:1. For our weak acids, the percent dissociation is different, a lot smaller, and we can't eyeball it and know what it is. So that's where our calculations later that we started last week with the ice charts come into play. But remember here, this is before dissociation. After, you still have a bulk of it is still the weak acid with a very small amount of ions. The Ka value, which is the ratio of ions over weak acid, is an indication of acid strength. So the stronger the acid, the more ions you're going to have, the larger the Ka. The weaker the acid, the lower the percent dissociation and the smaller the Ka. So we looked at this chart before break, and we see up here at the top that this Ka value, if you look back in your notes, this Ka value here is a lot bigger than the one down here. And so because this one is bigger than the one down here, this particular weak acid is relatively strong compared to this weak acid. So they're all weak acids, but weak acid strength is not the same. Our strong acids will include hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. Some textbooks also include the HClO3. And now you're seeing why I'm trying to avoid the pen, because I normally have really good handwriting and that is just terrible. So I will get more used to it as we go, but bear with me. Okay, so some books have this one in there, but for the most part, most references will just have these 6. The 7th one is borderline. HF, weak acid, it HClO, HNO2. So I can't list all the weak acids for you. So the best thing to do is to understand that if it's not on our list of strong, then it's weak. And last week in class, I gave you a list of weak acids that you should probably know by name and formula. Please refer to your notes. Strong bases will be metal hydroxides, so like lithium hydroxide, sodium hydroxide, and those are ionic, so they're 100% ionized. And then weak bases will include ammonia, and then there was a family of weak bases. Please refer to your notes on that, so that we had a full list of ammonia bases, weak bases that were related and similar in structure to ammonia. Okay, so we did this one last time, so I'm going to skip it, but you can answer this one on your own, but we did do this one in class, so I'm going to skip. We also talked about the autoionization of water reacting with itself to form H3O plus and hydroxide. And this is a is a reaction with a very small K value because very little water dissociates into ions in an equilibrium. So we did this last time as well. that if I look at the overall equation for the autoionization, we have a new K that's very famous. That's called Kw. And that is just products over reactants again, hydronium times hydroxide, and that equals 1.0 times 10 to the negative 14 at 25 degrees. So if we think of it as essentially an ice chart where this is X and that one's X, we solve for it, we get 1.0 times 10 to the negative 7 molar at 25 degrees. Okay, and those are equal. Everything will change if we add an acid into the solution or a base. So in an acidic solution, hydronium is greater than hydroxide. In a basic solution, hydronium is less than hydroxide. And then in a neutral, they're equal to each other. I'm going to click. And please go ahead and practice converting between hydronium and hydroxide. And so you can do these following slides on your own to just kind of review them. Okay. pH scale is for dilute solutions, and it's an indication of relative acidity. pH is the negative log of H3O plus. So remember that the higher the pH, the lower the H3O plus, and the less acidic the solution. And we saw this slide of some familiar solutions. So here's our bloodstream, which I talk about a lot at 7.4. Beer, 4.0 to 4.5. Stomach acid is lower pH. So as we move up into the blue range in this picture, we're going from very acidic to less acidic or more basic. Okay, so if Ka is an indication of acid acidity, let's take a look at some of the Ka values. So like nitrous acid, 7.1 times 10 to the negative 4. If we take the negative log of that number, so if I take, then I can find the pKa. Now bear with me with this pen. This is where things get scary. So let's take, if we take the negative log of this guy and its Ka value, we'll get 3.15. Please take a minute to make sure that you're plugging that into your calculator correctly. Notice that if we do the same for the rest of these weak acids, that the lower the pKa, the higher the Ka. And so pKa's will be incredibly useful. And we use them a lot in biochemistry and biology. So absolutely know and understand what pKa is telling us. You probably had the pH and pOH in previous courses. We started this last time. So just review these relationships. We did these on the board and review these. These will be kind of the least of our worries. And we did do these in class and we kind of practiced writing them out and talking about them. There's some practice ones that you can do from your homework. But basically the idea is that here's our neutral solution. Here is the concentration of H3O plus and hydroxide. Remember, those numbers came from these Kw. And then if we take the negative log of this, we get a pH of 7. If we take the negative log of the hydroxide, we get a pOH of 7. And then from there, the more acidic solutions will have bigger or greater concentrations of H3O plus, and notice what happens to the pH, it starts to drop. So you have an inverse relationship there. And then the other idea that you should definitely know is that pH plus POH equals 14. Okay, so please take time to go do these two sample problems. Sample problem 18.3, and to go back and forth between H3O plus and pH and hydroxide. And so we're going to spend a little bit of time on this. So let's take a look. We're going to calculate the H3O plus, pH, hydroxide, and POH for HNO3. So the first most important thing is to ask the question, well, what is that? And the answer to that is that is a strong acid. And strong acids, 100% ionized. Okay, let's take a look at calcium hydroxide. Question is, what is that? That is a strong base. 100% ionized. So you need to know your strong acids and bases. Without that knowledge, you can't set up the questions correctly. Okay, so we know they're 100% ionized. So I'm going to click. HNO3, since it's a strong acid, will completely dissociate. Calcium hydroxide, strong base, it'll completely dissociate. So let's think about how we're going to come up with their pHs with that concept. So one of the things I want you to think about is that the concepts drive the calculations. So I know these slides are a little bit cumbersome, but this isn't as hard as it looks, at least not right now. So see this point, 30 molar? Since it's 100% ionized, then a 0.30 molar HNO3 is a 0.30 molar H3O plus. And you just plug that number into here. And that gives us the pH. And we're going to be happy about that because what that means is our strong acids are easy to work with. Okay, they're easy calculations. Okay, and then the rest of this are those conversions that I asked you to review. That if I know H3O plus, I can always find hydroxide. If I know hydroxide, I can find POH. And so please review those simple equations. Those hopefully will become super easy for you. Okay, let's look at calcium hydroxide. So remember this guy, 100% ionized. So it means it's a strong electrolyte. For calcium hydroxide, for every 1 mole of the whole thing, there's 2 moles of hydroxide. So here, do you see this 2? That's because we're going to multiply the concentration of the whole thing by 2 because there's 2 hydroxides. So since the whole thing is 0.0042 molar, hydroxide's 0.0084 molar. And then we'll go ahead and plug that in. Okay, now that's a POH. And when we get our POH, I think the easiest thing to do is to just subtract it from 14 to find the pH. I know that this is showing it a little bit more roundabout, but that's just go straight for the pH once you know pOH. Okay. All right, pH probes are what we use to measure pH. And you'll see some videos on that in your lab. Okay, so let's talk about some important terminology. You learned about Arrhenius definition last week and in earlier courses. The Bronsted-Lowry definition is really an important one for us because what it says is that our acids are proton donors and that it donates H+. And a base is a proton acceptor and it'll accept H+. And so any acid-base reaction is a proton transfer reaction. So here is HCl, proton donor. It's going to donate it to those lone pairs on the water to make its conjugate base, an H3O+. Ammonia as a base is going to accept H+ from water to form its conjugate acid and hydroxide. Now notice what's amazing about water is that water can be both base and acid. So look closely. In this case, water is the base. Okay, it's going to accept it. So that means that H3O+ is its conjugate acid. So these two go together, and these two go together. Here, ammonia with its conjugate acid of ammonium, and then here's the water as an acid with its conjugate base as hydroxide. Okay. So let's just take a look at these relationships. For this guy, H2S, if you notice, let's look closely, it's donating it to ammonia. So H2S would be the acid, and this would be the base. HS minus would be the conjugate base, and ammonia would be the conjugate acid. Okay, the differences there are going to be 1H+. So we always will either add or gain 1H+ at a time. I'm not a fan of this particular slide. You can read it. It's a little busy for me, so I'm going to click on it. And I like this one better. Here's our HF. As our acid, it's going to donate H+ to water. That's the base. So here's our acid, and here's our conjugate base. And here's our base accepting H+ with its conjugate acid. Okay, so let's look at this one, for example. Here's our second reaction, HCOOH. Here's that carboxylic acid ending. That's going to donate H+ to Cn minus to make its conjugate base and conjugate acid. So let me highlight that, but that's what I mean by that. So study the rest of these. See if you can get the hang of them. Notice here, for example, 1H+ at a time. HPO42 minus goes to donates its H+ to SO3. Now you have then phosphate as the conjugate base of HPO42 minus, and then HSO3 is the conjugate acid of SO3 minus. But the most important thing I can stress is only 1H+ at a time. Okay, and so that's really important here, that you're not trying to lose two. Like, so for example, in reaction 4, it's H2PO4 minus, but you're not going to lose both of them. It's just one at a time. The other thing students struggle with are the charges on these things. So HF, let's go back up here to kind of look at that. HF is losing an H plus. That means it's leaving behind its electron. So make sure that you get these charges correct. Don't leave them neutral. So HF, if I look at, and I'm going to go on a crazy limb and try to draw a loose dot here. Okay, think about it, that if this bond splits, that you'd end up with F now with an extra electron, right? That's going to make that negative. Okay, and then conversely, water is neutral. I'm not sure if I should venture out to try to draw it, but here's water, it's neutral. If it gains an H plus, it's going to go to a plus charge. Okay, so what I would do if I were you is cover up this side and do all of these and practice the charges, making sure that you understand their charge relationship as you go from acid to conjugate base or base to conjugate acid. I'm going to do a little bit of a kind of super important the stronger the acid is, the weaker its conjugate base. And this will have some critical information for us later. So if I can do this without messing up, HCl, HBr, HI, HNO3, HClO4, H2SO4, HClO3, that's the borderline one, so I'll just won't put that on your test. Okay, so here, these are all strong acids. Can I abbreviate that as SA? Okay, so that means that they're conjugate bases. These are all very weak. And so if you look up here, let's find our friends up here. HCl, HNO3, okay? Those guys, if you notice, they're very strong acids. Their bases are very weak. So you see how this arrow going up shows acid strength. Going down, they get stronger in bases. So up here at the top, Cl minus is a negligible base. It's so weak. So maybe we'll add a very, very weak base. I'm kind of ignoring for a second our friend H2SO4. Okay, one H plus at a time. So its conjugate is HSO4. So here it is. Again, HSO4, really bad base. Now, our polyprotic acids like H2SO4, I'm going to address in a separate video. Its base, conjugate base, technically it's a conjugate base, but it's actually will still be acidic. But we'll come back to that. So let me highlight that guy. I'm going to say that that's our polyprotic. So that's in a separate section. Okay.